So starting with this example we used last time, there's actually one really key property that we'll see about kind of any MST that we find. One of these key properties is what we call the cycle property, which is if you have a graph with a cycle, then there's no way for the heaviest edge, the one with the highest weight, to be in the MST. So remember, a tree can't have cycles. So if we have a graph with a cycle to start with, we're going to have to choose some edges that don't form a cycle. So if we had this graph we used last time, it originally had a cycle, choosing a tree from these edges, we're going to have to break up this cycle somehow. So we're going to have to not choose one of these three edges. Now, why is that going to be the case? Well, we kind of talked about this before. Whenever you have a cycle, if you removed one edge, the graph will still be connected. So it's okay to remove one of these edges, but we have a choice in some sense which one to remove. Now, you could kind of go through and try removing, each possibility, remove that edge, remove that edge, remove that edge. And the world where you remove the edge with the highest weight, that's going to reduce the cost of the tree the most. And so your minimum spanning tree will never include the edge with the highest weight in its tree. So we'll always kind of be helped by removing this heaviest edge. And that's one way you can start thinking about these arbitrarily large graphs, thinking about how might you start approaching designing an algorithm or doing a principled approach to forming an MST. You can potentially start with cycles and start removing the heaviest edges because those can't be included in your minimum spanning tree. So now, this is one property that's going to be true about minimum spanning trees, is that if you have a cycle in your original graph, the minimum spanning tree will remove the heaviest edge from that cycle. That heaviest edge can't be there. There's actually another property about minimum spanning trees that we're going to use pretty heavily. This other property is what we call the cut property. So a cut of a graph is some separation of the nodes. So you might say, for example, one possible cut of this graph is to separate B into its own set and then have A, D, and C in the other. So a cut is just any partition. You partition the nodes into two sets, we call that a cut. The cut property says that if for any cut of your graph, so any partitioning, if you consider all of the edges that cross the cut, that go from one set to the other, so in this case, the edge AB and the edge BD, if you consider those edges, then the one with minimum weight must be in the MST. Why is that? Well, we're going to need some edge to connect the two cuts, right? Why? Because the graph needs to be connected, right? We have this set of nodes and this set of nodes. We need at least one edge to cross the cut to bridge them together. And so if we have our choice of edges to cross between these cuts, shouldn't we always choose the minimum to make a minimum spanning tree? And that's what the cut property argues, is that if you consider any cut of the graph, then the edges that cross it, the ones with minimum weight must be chosen for the MST. This should be true for any cut of the graph. So if you consider the same graph and consider a different cut, maybe separating A and B into one group and D and C into another, then you have these edges with weight 3 and weight 4, and you'd always pick the one with weight 3. You could also consider the cut of ABD and then cutting off C. That also would have to have that cut property, and that's kind of how we argue that we know we need to include that edge. There must be at least one edge between any cut of the graph. Whoops, I spoiled that a little bit. Notice that using this cut property, we can essentially, using the same graph, derive the same MST, right? So we'd say for, like, if you consider this cut, we would have to, oh, that didn't go to pen. We would have to include this edge outside of the cut that just contains B. Right? There's no minimum spanning tree that would not include this edge for this cut because it has the minimum cost. And if we consider this other cut, well, we would choose this edge with 3 going through it. And so you can kind of think about over every possible cut, we would end up with the same minimum spanning tree as before. It's just a different perspective of what minimum spanning trees need that ends up giving you the same result. And so we're going to actually see that the algorithms we're going to learn from minimum spanning trees work with these properties. The one we're going to talk about today is based off of this cut property, but the cycle property still can matter. It's still valid. It still tells you some cases, but the algorithm we're going to talk about today is really built on this idea of the cut property. So what do I mean by that? Well, what we're kind of going to have to do for some algorithm is think about maybe some set of nodes that we currently have what we think is the minimum spanning tree for. So we're going to start building up the minimum spanning tree. We know the minimum spanning tree that covers this set of nodes. And we need to somehow expand that minimum spanning tree to nodes that we haven't yet visited. So we kind of need an algorithm that maintained a set of known vertices and unknown vertices and repeatedly chose kind of the closest node to move from the unknown set to the known set. That sounds kind of like Dijkstra's, doesn't it? And it should. So we're going to use a modified version of Dijkstra's to solve this problem. So this is where we talk about Prim's algorithm. So we're going to do a couple adaptations to Dijkstra's to make it work for this case. The first being that minimum spanning trees don't necessarily have a source vertex or a start vertex. Remember, Dijkstra's, you're saying starting from this node, I'm trying to get to this node. You kind of build up the shortest path tree. Minimum spanning trees don't have a necessary start. Maybe in some examples they might, like where we have that electricity company, but in general, minimum spanning trees don't have a necessary starting point. So instead of talking about in Dijkstra's, where we talk about the vertices for which we know the shortest path from S, we're going to now talk about the vertices that are currently in the MST that we're constructing. So we're going to iteratively build up this MST, and we're going to keep track of the set of vertices that are currently covered, that we don't need to consider other paths to. And we're going to visit the vertices kind of that are in this unknown set based on the distance from those vertices to our MST under construction. And we're going to kind of change kind of how we define what's the distance to a node. That'll clear up in a little bit. Now, one thing I'm going to mention as a bit of historical note, Prim's algorithm was actually discovered multiple times. It was first discovered a long time before Prim by someone named Jarnik. And it was independently rediscovered by Prim in 1957, actually before Dijkstra's. Dijkstra's actually was kind of modified from Prim's in some sense. And so sometimes you might hear it called Jarnik's algorithm or Prim-Jarnik algorithm, and sometimes people include everyone's name, the DJP algorithm. We're going to call it Prim's for simplicity, and that seems to be the most common name that's used, but there's a bit of a historical interesting note there. So Prim's algorithm is going to start kind of the way we're going to think about it, is it's going to start exactly like Dijkstra's. So here's the exact code for Dijkstra's shortest path from a start vertex to an end vertex. Now we're going to modify this slightly to kind of take into account this idea of we're currently building up a minimum spanning tree, and we want to include a node that's closest to this minimum spanning tree. We're going to, again, remove the notion of the shortest path from a start vertex to any particular node. Remember, we don't care about start vertices anymore. We're just saying we have this MST under construction. Now find me the next closest node outside of that, the nodes in that MST to include. So Dijkstra's is built off this shortest path from the start. That dist2 map stores what we think is the shortest path from the start node to any particular node. But we don't care about that, so we need to modify how we think of dist2. Now, what we are going to be thinking about for prims is we have this set of known nodes, this MST under construction that we know the shortest, the MST for. We have this unknown set. So the node and the edge we want to include is the smallest edge that connects the cut between the known nodes and the unknown nodes. And so what we're going to end up doing, the only change we have to make for prims is we change our definition of new dist. Instead of making the new dist be the distance to get to node U, the one we just added, plus W, the weight of that edge, we just say, hey, we're going to consider the edge weight right here. Now, why do we do this? This is probably unclear. So Dijkstra's and prims have this known set. The known set is expanding. It's kind of the set of all nodes that we currently know the shortest path to in Dijkstra's case, and for prims, the minimum spanning tree for. And this forms a cut in the graph. The cut being all of the known vertices and all of the unknown vertices. And using the cut property, a minimum spanning tree for the whole graph must include the smallest edge weight that crosses this cut. So in this little example here, where I have nodes B and C in my known set and A and X outside, and we have all of these edges going from the known set to the unknown. And here I am showing pictures of directed edges, but that doesn't necessarily matter. The cut property would say, hey, we want the shortest edge. We're going to include that because minimum spanning trees must take the shortest edge between any two cuts, or for any cut must take the shortest edge that crosses it. So the way we change Dijkstra's is we change the definition of what's the new distance to a node. Instead of keeping track of the path length from the start vertex, we define the distance to the node as just, well, what's your shortest edge length from the currently known set to you? So we just take the edge weight itself. Besides that, everything's the same as Dijkstra's. I guess I should also change the method header to not include the start, which is what which I will make sure is fixed in the slides afterwards, because we don't have a start node necessarily. Oh, actually, I take that back. We have to pick some node to start with. You could pick arbitrarily. We'll talk a little bit more about that in the class session or with a practice problem about how to choose start. But right, we do need a start node for prims, but it's not part of our distance calculation. So this has been kind of weird and abstract. Dijkstra's, but not. Let's walk through an example, and hopefully this will make a little bit more sense of how we go about this. So I have my graph from earlier. And let's suppose I have my prims code. It's, Dijkstra's, but I already made the changes. So this is prim's algorithm for finding a minimum spanning tree. So we start off a lot like Dijkstra's. Remember, the only thing that really changed was that update step. So we start off by initializing all of the nodes to be infinite distance away. And we're going to suppose that F is going to be our starting point. So we're going to say that's distance 0. Now, just like Dijkstra's, we grab the node that's the shortest distance away, and we go mark it as known, and then update all of its neighbors. So we're going to update all of F's neighbors, D to be distance 8 away, C to be distance 10 away, B distance 6, and E distance 9. So far, nothing different than Dijkstra's. Now, when you start getting to your other iterations, things start getting a little bit different. So the way this is working here is we've chosen F. We kind of have added F to our known set. And now what prims is going to do is find the edge that kind of crosses this cut, include that edge in the minimum spanning tree. So the next node that's closest is B. So we're going to mark B as known, and we're going to update all of its neighbors. So let me quickly start by drawing B in this known set. So now this known set kind of looks like this. Now we need to update all of B's neighbors. So B's neighbors are A and E. And so I define the distance of A to be 3 and the distance of E 2. Now, this is where it's different than Dijkstra's. Because you might be wondering, whoa, wait. In Dijkstra's, don't we have to update the path to A to be 6 to get to B, plus 3 to get to A? And that's entirely right for Dijkstra's, but Prim's doesn't care about path lengths. Prim just cares about finding a set of edges with minimum weight that connect the graph. So we don't want to say the distance to A is 9, because that's the distance to get from A to the power plant. We don't care about the distance to the power plant. We just want to connect A to our graph. And so we're going to find the distance as being the distance to any of our nodes in our node set. So for the nodes that we've added so far, what's kind of this shortest distance? And our dist2 map is going to be keeping track of that. It's going to keep track of whenever we add a node to our node set, we're going to go to all of its neighbors and say, hey, is there a shorter edge weight to this node that I can update for dist2? So that's very, very important for prims, is that we don't consider the entire path length. We just consider kind of the edge weight itself. But besides that, it operates exactly like Dijkstra's. So we continue, grab the next shortest distance node. In this case, it's going to be E, and we're going to update all of its neighbors. So E found a shorter path to D. Remember our original shorter path? Sorry, I shouldn't say shorter path, shorter connection. Originally, our shortest connection to D was starting at F and taking that edge weight of 8. But now that we've included E in our minimum spanning tree, we found a shorter edge weight, 7. So we update our dist2 appropriately. Then we grab the next closest node, which in this case will be A. We update all of its neighbors. So A, there's an edge weight of 1 going from A to C, which beat our old 10. So we include that. Again, very weird how similar it is to Dijkstra's, but we're not including entire path lengths, just edge weights. And we just keep going, so on and so on. And then finally, once you've kind of run all of Prim's algorithm, you have this whole table built up, you can reconstruct the shortest path tree. So, or the minimum spanning tree, I should say. We have D. How did we get to D? We got there through A. We got to C through A. We got to A through B, B to F. And so this defines the set of edges that form the minimum spanning tree. And then if you want to find the cost, you can go through and add all of these up. Now, one thing you might be a bit worried about is how do you know which node to start at? Prim's algorithm works starting at any node. And part of the reason for that is the cut property, right? The cut property applies for any cut. So you can imagine the cut starting with your starting vertex. Any starting vertex you choose will form a cut, and that cut property will have to hold. So you'll always find the global minimum spanning tree. There sometimes might be duplicates, or there might be multiple minimum spanning trees, but that will only happen if you have edge weights that aren't unique. So then you have like a choice in some sense. Do you want to take this edge that's weight 1 or this edge that's weight 1? You'll end up with the same cost, the minimum cost, but you might get slightly different trees. But Prim's algorithm will work. It will always find the minimum spanning tree. Now, in terms of runtime, the runtime for Prim's is going to be exactly like Dijkstra's. Remember, the only line of code we changed was this new dist calculation, which we considered a constant line of code anyways. So Prim's algorithm runs just as fast as Dijkstra's, which is really, really great. So to help you conceptualize a little bit more about how Prim's and Dijkstra's are similar but different, I want to show you one animation that might help you think a little bit about ways to compare and contrast them. So here I have two videos I'm going to play side by side. On the left is Dijkstra's algorithm running, and on the right is Prim's algorithm. And they're going to be doing a lot of the same things. They're starting at some source vertex, and then running their algorithms, marking all of the nodes as visited by coloring them in black. So you can see that Dijkstra's and Prim's explore the graph very, very differently. Remember, Dijkstra's is always choosing to include a node that has the smallest length from source to that node. And so as you get further and further away, like you're adding longer and longer distances. And so it was really going to be kind of exploring radially in some sense. Now, it's not a perfect circle because it depends on the edge weights, but for Prim's, it only cares about the edge weight. It doesn't care about the sum of the edge weights along the path. And so it's going to kind of just go off and keep grabbing the smallest edge over and over again, which maybe will let it explore the graph much more fully. So this this animation will be there on the slides if you want to watch it again. I can go back and play it while I'm still talking. But this is really kind of like, they're so similar in the sense that they're searching through the graph, adding things to the known set. But the way they do it, even though their code is so similar, is very quite different. And that, again, that big difference is how do you define the distance to node? So that's all we have to talk about for today. In class, we'll practice some of this stuff about minimum spanning trees and prims. And then next week, we're going to introduce a new algorithm to find minimum spanning trees called Kruskal's algorithm, and a new data structure that we'll use to support that.